keep in mind that this time they will consider attendance for the attendance marks, and also if you are not going to attend the class, you are going to face a lack of attendance. Keep in mind that. Please inform to your classmates, ask them to attend the class regularly, and don't later don't carry any other things. Okay. Okay. So now we'll be moving forward. So in the last class, we take up the we take up the your low speed wind tunnel. Wind tunnels, okay, and we looked into the your these options. Okay, what are the components of that for both? Okay, your open test section as well as closed test section also. What are the components, how it is each is concerned. Then we looked into that. Okay, what are the instruments used? Okay, for doing the sum of the one. So one is your, we talked about that your pitot static cube. Another is your your flow angularity. And next is your, what is the other one? Your total flow. That's also coming under your static flow. Okay, total flow. Even the flow angularity, 3-hole probe, 5-hole probe, and your 7-hole probe or omni probe. So these points we have seen that. Okay, so these are the things we have seen that. What is the purpose of your total probe? It's for your boundary layer thickness measurement and all in the test section wall. How are we going to measure that? Okay, in a wall, okay, a particular location. If you want to measure the thickness, okay, we are going to keep the particular X location. Okay, we are going to vary the Y location. We are going to capture the your P naught, okay, and we are going to use the whatever the your P available in the undisturbed stream. So we are going to use these two, and we are going to get the your velocity. Okay, so your P naught minus P is equal to half rho V square. Okay, so this is your incompressible form of Bernoulli's equation. We looked at that. We have seen that one. So even already, okay, in the Viva also I asked about that your different boundary layer thickness, your displacement thickness, your momentum thickness, and your energy thickness. Okay, so these are the your three types of your boundary layer thickness. Okay, using that only we are going to do that. Okay, already even one of your classmates explained to me very clearly. Okay, your displacement thickness means your mass flux loss, the changes, deficit in mass flux, save momentum, energy. Those things we are going to measure in terms of due to your boundary layer. Okay, so those things we have seen already. Okay, so and also another one more thing that we have to know is your in the tunnel measurement. Okay, if you look at that, okay, in the your test section walls and all, we'll be mainly looking at that. Okay, for example, if you have a test section, okay, so one thing is, okay, we are going to measure the your turbulence. Okay, turbulence within the your this one. What is the turbulence? Okay, the turbulence, if you look at that, for example, if a hot wire anemometer, if I am going to keep it inside, okay, so using the hot wire, what I can do is an instantaneous velocity, I can measure it. So basically, these whatever this line, it's going to talk about that your mean component. This is going to be your instantaneous component, U dash. So U of t, it's going to be U mean, okay, So plus U dash of T. So that's what is going to happen in the case of your this one. So this is a way we are going to see that your turbulence level. Okay, that is a your pressure sphere. I'll come back to that. Okay, your later. Okay, pressure sphere and your turbulence measurement and all. We are going to do that. We are going to look at that your critical Reynolds number. Based on the critical Reynolds number, what is your CD value? Okay, and how it's going to be related to the real time condition. Based on that, they are going to measure the turbulence factor. Turbulence factor or turbulence intensity. Okay, from that we can get that turbulence. Other thing that, okay, if you look at that, okay, vertically I can go ahead further. Okay, I'm going to see that, okay, how my velocity or a static pressure distribution, whether any gradient in the your test section. For example, while moving from y for a particular x, or while having a flow quantity here, we are going to see that, okay, any gradient in your pressure. That's okay. That is because of, okay, design or fabrication instantaneously pick up something. Okay, that's going to induce some kind of pressure gradient across the vertically or across the your x and y directions, x, y, z direction, all three directions. Okay. Yeah. Any question on that, sir? Any question here? Any question here? Okay. So next thing is, okay, we have seen that, okay, your incompressible flow, okay, subsonic tunnels. Basically, we looked at that, okay, until now we have seen that, okay, what is going to be in the subsonic tunnel. Subsonic tunnels. So in the case of a subsonic tunnel, okay, how, okay, what are the instruments we are going to use? I'll come back again, okay, each and every equipment, how are we going to design, okay, and how your design features for different your subsonic or supersonic conditions and all. So accordingly, we will go ahead further. What could be the possible losses in each cases, okay? Those things and all, we will look at that in detail, okay? How we have to be very cautious, okay? Those things. So now let us go for your supersonic tunnels. Let me finish the supersonic tunnels, okay? Then we will consolidate everything. We will go as your instrumentation part of that. One is, okay, your blow down tunnel. Second is your in draft. And third one is your continuous tunnel. Okay. So first let us look at that. We will give a more importance for your blow down tunnel and in-draft tunnel. We will be looking at that. Okay. So basically in the case of a blow down tunnel, what we will use is we will have a compressor. Then whatever the air coming out of the compressor, that's going to pass through your dry air. Then it will go to your pressure vessel, air storage vessel. Air storage vessel. Okay, it will go to that. Again, they will be having a flow control valve. Again, okay, you have a fine pressure relief valve, fine control valve. Fine control valve. Then it will go to your settling chamber. From the settling chamber, you are going to have a convergent divergent nozzle. This is your settling chamber. Convergent divergent nozzle. Then you have a test section. And this is your test section. And then afterwards, okay, they used to have a another one more this one, convergent divergent nozzle. Okay, normally what we call it as a second throat. Second throat. And then afterwards it will go into the your silencer part of it. Your silencer. Basically, normally if you look at the high-speed flows, okay, sound will integrate part. So first is you are going to have your compressor. The air is going to be absorbed from the atmosphere, okay, with a filter. It's going to be absorbed here, okay. So and filtered, and it's going to be with the help of a compressor. It's going to be compressed. The advantage, okay, then it will pass through the dryer. So the purpose of the dryer is, okay, if you look at that, okay, any air, it's going to have a mixer. Water vapor, it's going to be automatically, it will be there. So we need to remove the your air from water vapor from the your air, okay, whatever the compressed air. The reason is, okay, if you are not going to remove the your water vapor, automatically all those valves and tanks and all these water vapor will go and sit, and it's going to corrode those valves and makes sure that, okay, it's going to malfunction of the valves and all. It's going to take place, one thing. And it's going to, in the air storage tank also, it's going to create a rust, and it's going to affect the life of your durability of your air storage tank. So depending on the, okay, how much amount of pressure range you are going for that, whether 200 bar or a 250 bar or a 100 bar, accordingly you have to choose your dryer, and how fast your velocity is going to decrease. Sorry, how fast, okay, you are pumping, those things and all, you need to look at that. Okay, here you need to see that mainly a dew point. Dew point. Okay. So we need to see the dew point here. Okay. So then what will happen afterwards? This dryer, okay, whatever the air, dried air, it will go, and air storage vessel, we are going to store it here. Okay. So now what is going to happen here in the air storage level? A pressure relief valve will be there, your PRV, and also your pressure gauge also will be there. Pressure gauge will be there for indicating that, and also a drain valve will be there. Okay, if there is any drain valve. Okay, then, okay, we have to store that as much as amount of pressure. Okay, depending on the your tank volume. Okay, I have stored it in a tank. Okay, air, but I am going to blow down through a convergent divergent nozzle here. I want to know how much Mach number I am going to achieve, first thing. Second thing is, okay, how much amount of, okay, your blow down time. Okay, Mach number, and in the test section Mach number, and how much for the stable for that particular Mach number, how much the blow down time I am going to happen. That and all, okay, it's going to be dictated by the your atmospheric pressure, atmospheric conditions, basically atmospheric pressure, temperature. Okay, first thing. Second thing is mainly your pressure vessel stagnation pressure, and your stagnation temperature, and your tank volume. Okay, your tank volume, and also, okay, stagnation pressure, stagnation temperature, volume. And other than that, okay, your throat area of the nozzle, your test section area. So these are the factors are going to dictate your test section Mach number, okay, and your flow down time. So whatever the your CD nozzle, okay, nozzle flow through nozzle available in our lab, this is going to talk about that. This is what the one it's going to talk about that. Okay, we have that same thing. We don't have a dryer. We have a compressor, and straight away we are connected to a pressure vessel, and we have a flow control valve that's going to the settling chamber, and we have a convergent divergent nozzle, and we have a test section. But afterwards we don't have a second convergent divergent nozzle or a convergent divergent diffuser. Normally we won't call it as a nozzle, we will call it as a diffuser. Okay, so those one, okay, and also we don't have a silencer unit also in that. So we have until your test section part. So anyway, part of your propulsion lab, you need to study about the flow through nozzle. You need to estimate for a particular flow down condition, how much amount of Mach number you are getting. Those things we can get that. But our lab facility, we don't have a Sleren system, but right now we are going to buy that Sleren system. Everything we are going to buy it. So maybe for your lab, we will be using the Sleren system. Okay. Any questions, sir? Any question? Any question? So, if you refer instrumentation, measurement and experiments in fluids by Radhakrishnan book, okay. So there you can find out what is advantages and disadvantages of that your blow down tunnel. Okay, please read that and keep in mind it's going to be useful. It's a self-explanatory. I'm not going to take up that one here. Okay, so you proceed with that one. Okay, you proceed with that one. So basically, this is having a comparatively better advantage with that one, but certain disadvantages are there because here we are going to have a compressor, so it's going to have a, okay, whatever the exhaust coming out of the compressor, okay, it's going to have oils also, that's also going to be there. Okay, and other issue is, okay, while blow down your pressure, automatically your temperature is going to drop down, so automatically your test section Mach number is going to affect. So you refer that book, okay. Still, if you have any question on that, we will discuss in the next class. Okay. Yeah. If you don't have any other question, then I'll jump into the next part of it. Any other question? Any other question? Okay. Next is your in-draft tunnel. Okay. So here, what we are going to do is, okay, first is we need to have a dryer, and we'll be having a settling chamber, dryer, a settling chamber, and from the settling chamber you are going to have a convergent divergent nozzle. From the convergent divergent nozzle you are going to have a test section. So if there is a necessity, they will go for another one more convergent divergent diffuser. So basically it's a diffuser part of it, and they are going to, this is your test section, this is your CD nozzle, and this is your settling chamber. settling chamber and your dryer. Then sorry. So they are going to put up a valve and they are going to connect it to a vacuum chamber. A vacuum chamber. Vacuum chamber. So with the help of a pump, okay, vacuum pump, we are going to create a vacuum inside. Whenever you want, okay, with the help of this valve, you open that, automatically flow is going to be established through the tunnel. Okay, you are going to have a test section. In the case of your blowdown tunnel, a Mach number of, okay, you are going to have you can achieve something close to 4. But in the case of an indraft tunnel, you can achieve more than 4 also. You can achieve a Mach number of more than 4 also can be achieved in the indraft tunnel. Okay, so the purpose of the second throat is basically, okay, like whatever the way in the case of your subsonic tunnel diffuser, same thing. It's going to recover your static pressure from your kinetic energy, converting your kinetic energy into pressure energy, pressure recovery. So automatically your work requirement, power requirement will, with the same load on mass, you can achieve a higher capability, more amount of load on time. Okay. Any other questions, sir? So just look at that book. Okay. Here also you can compare your both your merits and demerits. If you have any questions, you can come back.
Sir, what is the difference between supersonic and shock tunnel, sir?
Sir, both are same, sir. Okay. See, the construction wise is going to be different, sir. Shock tunnel. Okay. One type of supersonic tunnel. You are asking about the shock tube. This is a shock tunnel. What do you mean by shock tunnel? I heard about shock tube, but what about your shock tunnel? This is a supersonic tunnel. It's basically your indraft tunnel and blowdown tunnel and all a supersonic tunnel. You are going to achieve a supersonic flow. Shock tube is something you are different. Okay, so there you can go for a multiple reflection of shocks. Based on that, okay, I'll take up that shock tube and all separately with the diagram. Okay, I can take up that. So mainly, okay, what we are going to do is, if you take a normal shock, successive normal shock, okay, so what they do, because of that shock, okay, they are going to depend on a fast moving or a slow moving shock wave. They are going to merge together while passing through the medium. It's basically a moving shock, okay, passing through the moving shock, okay, passing through the medium. And what will happen across the shock? Your static temperature will increase. Static pressure also going to increase. Okay, because of the increase in temperature, okay, whatever the material, it's going to be exposed for a certain duration. For example, a body is going to re-enter into the atmosphere for a particular Mach number. Okay, if you look at that, that's going to be minimum time. How it is going to be eroded, all it's taking place. Whatever your thermal barrier coating that you placed underneath your blunt body edges, how it is going to change. That and all studies. Or for example, you have a high energy material, combustion material. What is the exhaust? How the burning is taking place?
Okay.
Okay, the shock is going to move over the medium, so automatically it's going to create a high temperature. Something close to, depending on your strength of the shock. Basically, strength of the shock is, okay, if you look at the across the shock, your pressure is going to be P2 by P1. So the shock strength is going to be P1 minus P2 divided by P1 percentage.
Sir, all the static properties, do they increase across the norm existing moving shock, sir?
Yeah, same. Whatever the one is going to take place for the normal shock, same thing is going to happen for the moving shock. So here the medium is going to be stationary, only shock is going to move. So what they will do is, okay, both of the end, they will create a your pressure difference. One side they will have a pressurized medium, another side they will be having a vacuum chamber. So in between that, a thin membrane will be there. Okay, diaphragm, what they call it as a diaphragm. The moment they burst the diaphragm, they will be having a method to burst the diaphragm. Okay, so automatically what will happen? Yeah, fast moving air is going to be established from the pressure vessel towards your vacuum condition. Automatically your speed will be more amount of shock will be generated. So depending on your pressure difference, automatically you can have a higher strength.
Okay.
Automatically your temperature also going to be higher. So you can do the energy studies.
Okay, sir. Okay. So this gate, we had a question on moving shock.
What is that, sir?
This gate exam, we had a question on moving shock, sir. They said shock is moving and they moved the reference frame also. So it became a stationary shock problem. And then they asked us to relate the properties upstream and downstream.
Mm-hmm. Normally compressible flow, okay, it's an important one.
Yes, sir.
You have to, first of all, you have to convert as a moving from frame to static frame. Then you have to establish, okay. Then you have to bring back again to your moving sock. Then only you can find out the property. First of all, you have to convert your moving sock into a stationary frame, moving frame into a stationary frame. Then you have to do that.
Yes, sir.
Anything else, sir? Okay, so now I'm going to give a task to you. Okay, I stop the session here. Okay, so what you can do is you take up your indraft tunnel and blow down tunnel. What is the advantages? What is the disadvantages? Refer the paper, your book. Okay, instrumentation. Please don't copy from others. Okay, just to you have a Gen.library book will be there. You need to have I need to see all of them's assignment in your my teams. Okay, I'll put a folder here right now. Okay, I need to see that. Okay, I need to see all 30 assignments. One is, okay, what is the advantages and disadvantages between your blow down tunnel, indraft tunnel, how the construction is going to be, and what is the schematic diagram, and what are the components are there. I need that. What's your next hour class?
Next hour we are free, sir.
Okay, so 1, 2, 3. Then that's all. Today no class.